Hey, Katie.
Hi, Ben.
How you doing? What are we talking about today?
We are talking about the grammar of graphics.
The grammar of graphics.
Yeah. This is a visual episode in audio form. So let's see how this goes. It's going to be interesting.
Okay. You are listening to Linear Digressions. Okay, so I know what the term grammar means as it applies to language.
Mm-hmm.
It's kind of the rules about how you would construct sentences, and I'm sure that there are many people who could define it better than me, but that's kind of how I think about it.
Yeah, that when we are using language to communicate, there's an order in which we place subjects and verbs and objects. There's a recursion to language in the sense that you can have phrases that have substructure. There's also orders in which things tend to appear. Like I would always say the big black car. I would never say the black big car. Grammar is, this thing that's a little bit hard to define, but once you start to think of it, it's pretty common to think of it in terms of the rules of language.
I actually was reading something really interesting about this. I just found a tweet by Matthew Anderson, things native English speakers know, but don't know why we know. And the quote is, adjectives in English absolutely have to be in the following order: opinion, size, age, shape, color, origin, material, purpose, noun. So you can have a lovely little old rectangular green French silver whittling knife, but if you mess with that word order in the slightest, you'll sound like a maniac. It's an odd thing that every English speaker uses that list, but almost none of us could write it out.
Yeah, I think I've heard something similar too. So I think that was what I was like drawing on a little bit in that example.
Right. Green great dragons? No, great green dragons.
Yeah, exactly. So, but we're not talking about language in this example.
So
Instead,
what
we're
does
talking about
this
the
mean?
grammar of graphics. Yeah.
Yeah, what does that mean?
Yeah, so that's what we're going to spend the next 15 minutes talking about a little bit. But the rough idea here is that, so just like there's an expectation that you have about the word order or the construction of phrases when you're listening to someone speak or when you're reading a sentence, there's a similar idea perhaps for drawing visualizations of data or consuming visualizations of data, things that you expect to see whether or not you even really think about it, or when you're composing a visualization, things that you're planning for or taking into account that, again, maybe you aren't thinking about, but this comes up in a really deep way if you are, say, dealing with data visualization software at a pretty fundamental level. So for those of you who are into the R universe and particularly the tidyverse, Hadley Wickham's corner of the R universe, you're probably familiar with a package called ggplot2, which is a visualization library in R that's kind of famously makes very beautiful graphics, especially with its defaults make for really nice graphics. The GG in ggplot2 refers to grammar of graphics, and actually, yeah, the most of the research that I did for this episode was reading a 25-page paper that Hadley Wickham wrote about how he thinks about and how the field in general thinks about the grammar of graphics for data visualization. So that's what we're going to talk about.
Very cool. I don't even know where to start in thinking about this. This is going to be neat.
Yeah, this was a pretty challenging topic for me to try to understand because it gets into theory pretty quickly of like, what is a facet and what is a scale and what's the difference between a mapping to an aesthetic and a coordinate system. I think there's certainly a lot to unpack if you're just really excited about this idea, but rather than getting into some of these kind of esoteric concepts, especially concepts that are esoteric without having examples to look at, I wanted to illustrate the main pieces of the grammar of graphics as Hadley Wickham, for example, talks about it, using an example of a visualization that probably a lot of people are really familiar with and how that illustrates a few of the big important concepts that, again, we all kind of take for granted probably in our day-to-day visualizations.
Okay. So what's the example graphic then?
All right, let's talk about a stacked histogram.
A stacked histogram.
Yeah.
Can you describe it for me?
Yes. So let me give you an example of stacked histograms that I used to make all the time when I was a physicist. So when I was a physicist, we used to make lots and lots of plots where what you were trying to do was look at distributions of particles that you were getting in your detector. And in general, there were lots of different kinds of particles that were classified as what we would call background. So these were types of particles that were, interesting, but not what we were really searching for. And then there were, in certain situations, you would be looking for signal particles as well. So this might be like a Higgs boson if you were doing a Higgs search. And so when you were creating visualizations of your data, what you're looking for is, okay, do we have a distribution of data that's more consistent with there only being background present? Or does it look more consistent with background plus signal? Where the second case is like, oh, maybe we discovered some new physics or something. Mm-hmm. So we would think a lot about how to visualize background. And when you're doing that analysis, you tend to have different kinds of particles that are coming in from, say, different places in your detector. And so if you just look at one of those systems at a time, you're going to get an incomplete picture of like all of the particles. Instead, what you want to do is layer them all on top of each other so that you so that you have like a picture of the overall distribution of the particles that you see, but you also have them stratified by the different types of physics processes that they correspond to. And so you're kind of stacking each of those strata on top of each other, and you have a visualization that shows, each of them separately, but also all of them adding together. That's roughly what a histogram is.
Got it. I think I've seen these before, or I'm sure I've seen them in many places, but I'm thinking about when you do a software release and you look at all of the different computers that are running the software and what version they're on, and you can see how people have upgraded. Each version of the software will be represented by a different color, and over time you'll see them kind of go and peak, and then as new software later is released, then the previous version will kind of trail off. And the representation that you're talking about is showing all of that in a single graph with time, let's say, being the x-axis. And in my example, it's always at 100% height because every user is on some version, but you can see the distribution at any given point of those versions.
Yeah, or if you decided to represent it instead of as a percentages of the whole, if you had your y-axis was allowed to float and instead it was the total number of users using that system, then you could imagine like the overall rate could actually go up and down as users join and leave your system or are using your software or whatever.
Okay,
yeah.
So I have an image in my head now.
Okay, great. And so hopefully for most of the folks who are listening to this, hopefully you do too. But if you don't, or if you're really struggling to think about what a stacked histogram might look like, it might be worth taking like 5 seconds to Google this on your phone just so you have like a mental snapshot, because I don't imagine that the rest of this will make tons of sense if you have no idea what we're talking about. So, okay. So stacked histogram. How do we think about this in terms of the grammar of graphics? So let me layer in a few of the fundamental ideas of grammar of graphics. So these are taking place in a very explicit order. So the first layer, the most foundational layer of when you need to make a data visualization is what is the data set that you're going to be visualizing, and how does that map from the variables in the data set to a set of aesthetics. So what's the data set? Let's talk about that first. Let's use my example of, let's use your example. Actually, I think that's probably like a little bit more familiar to our listeners than like a particle physics data set. But instead we have some notion of a data set that has all of the users of our software through time and the type of, what did you say it was, like the version of the software that they're using?
Yeah, and actually, can I make this a little bit meta and tweak this? And we'll say this could be linear digressions episode downloads. Like we can go into our hosting provider and we can see how many people download on a given day. And so, of course, the day after we release an episode, we see a lot of downloads, and then maybe, 2 months go by, and now that episode is a small sliver.
Yeah, no, I have seen that, right, where you see like a spike on the day after an episode is released, and then it tapers off. But of course, there's a new spike that pops up the week after because that's the next episode. So there's kind of like layers of these decaying distributions that sit on top of each other. And so if you want the total number of downloads for any given day, you have to add up the contributions from all of the different episodes, the one that dropped the most recently, but then there's probably also some episode from last week that's still getting some downloads. There might be an episode from a few months ago that there's a new listener who just subscribed and they're downloading some stuff from the backlog. So there might be little contributions from those. So yeah, you layer them all on top of each other. And then that all adds up to the total number of downloads that you have for the day.
And to get that total number, you just look at the top of the graph at that point.
Exactly. Right. But you can, break it apart into each of the component layers, right? Okay, so let's think about the underlying data set if you're SoundCloud that's keeping all of these download records in its core form. What that probably looks like is a table that has a few columns. It's like some identifier number or the title of the episode. So it's like, which episode is this? It's the day and probably the time that it got downloaded. And I think that's all that you need. So then when you're creating the histogram, you're working with that as your default data set. And we said the second thing that you need at this level, you need a default data set and you need a set of mappings from variables to aesthetics. So what are the aesthetics that we have here? Well, we have some notion of the left to right dimension of the histogram is through time. So we have some kind of notion that where a data point gets represented left to right gives us some kind of information about when it happened in this case. So that's an aesthetic choice. And one of the other notions that is worth introducing at this stage, but we're going to really develop in the next step in terms of aesthetics, is that there might be different colors for each of the episodes that we want to represent. So maybe the episode that I released today shows up in my histogram as red, all of those downloads. But then the one that we released a week ago might be in yellow, and one from the week before that might be in blue, so that when you actually look at the visualization, if you have a stacked histogram, but all of the stacks are the same color, then you're not going to be able to visually distinguish them. So there's also this notion that there's some way of mapping each of the different data points onto some kind of aesthetic representation. So in this case, we're kind of giving the example of color, but it could also be like in the case of if you're doing a scatter plot, it could be like, are these stars or are they little circles or triangles or whatever? Okay. So we have our default data set. We have a mapping from the variables to something that's like aesthetically, how are they being depicted in the graph? Second component of a grammar of graphics is introducing the notion of layers. So again, explaining this by example more so than by abstract definition, you can think of a plot not as being everything is just dumped onto a set of axes or whatever, but instead that each of the different things that you want to represent is kind of like a layer of visualization that gets put on top. So in the case of a stacked histogram, we don't have the notion of, at this point yet, that there's necessarily multiple different histograms that we want to depict. Instead, we kind of are starting with like each different episode gets its own histogram, and we want to be all displaying each of those histograms one on top of the other within the same graphic. Does that kind of make sense?
Yeah, that makes sense.
Okay. So for each one of these layers, each one of them is going to be layering on a different piece of the visualization. So for each of them, we're saying like, what's the geometric object? So that means like, how are you actually drawing this? So in the case of a histogram, it's bars. You're actually drawing like bars where the height of the bar represents something, some aspect of the data. There's a statistical transformation. So when we draw a histogram, we're not just drawing the raw data points themselves, but rather we're drawing a there's two things that we do when we draw a histogram. First of all is that we're defining some notion of a bin width, which is saying like how are we bucketing the data? And then
like
a histogram
per
is
hour or per day.
Exactly.
Right.
And then a histogram is that bin, that notion of the binning, plus the operation of counting all of the data points that fall within that bin, and that gets mapped onto the height of the geometric object, the height of the bar. So we're doing actually something pretty complex here with the data. We've gone from this like long tabular format into this transformation that gives us a notion of a bar that's got a height, and then there's a whole bunch of bars that get stacked next to each other. That's our definition of a histogram. So it's actually, like I said, these are things that like we look at it and it just clicks for us. But when you think about that transformation, it's actually, there's like a statistical operation that's happening under the hood there, which I think is really interesting. Okay, so we have our geometric objects, which is those bars. We have the statistical transformation, which is how you go from the raw data set to the bar. Mm-hmm. Third thing is a position adjustment. So this is where I think, especially thinking about the different layers, it starts to get interesting. At this point, we have not yet introduced the notion of the offset, the stacking aspect of the histogram.
Oh, interesting. I see. So if we're talking about drawing the 4th episode back, it's not the one that's going to go on the bottom. It's going to end up being, on top of the previous 3 episodes in our drawing. Or if we do it the opposite way, it'll be on top of all of the episodes that came before it or after it. I got my so it's kind of like confused.
If you make a mistake, I made just like a really rookie mistake with a stacked histogram. This was just a couple weeks ago, actually. So I made a histogram and I didn't think about this position aspect of it. And instead what I did was I had like 6 different categories that I wanted to plot. And I just plotted like one after the other, like 6 in a row. And then what ends up happening is whatever you plotted most recently ends up on top. The thing that was plotted right before that ends up a layer behind it. The thing that was plotted before that ends up a layer behind that. So what ends up happening is like if your biggest bar is the last one that you plot, then that's the only thing that you see because it's covering up all the layers that are underneath it. They're just hidden behind.
Vice versa, if your smallest one is more recent and your biggest one is further back, you might think you've drawn a stacked histogram. But in fact, that
was actually my clue. Was I was looking at it, I was like, wait, I'm only seeing like 2 colors here. But it was just the 2 most recent layers that I had drawn. And I was like, that doesn't make any sense. So in this case, there's this notion of the position of the histograms. Each one has to be offset on top of the ones that you have layered before, so that instead of just being smack on top and covering them up, instead they're like incrementally growing on top of it, which is actually a pretty complex operation if you're starting to think about it. Like from a programming fundamentals perspective, you have to be keeping track of like, where is the position of the top of the bar at this point? And that's where the bottom of your next bar goes in so that it can sit on top. Mm-hmm. And, again, it's a very intuitive notion for our brains, but in terms of like, how do you represent this in computer code in a way that like always works? Non-trivial.
I also go immediately to, that sounds like an exponential operation if you solve it naively. So you might have to do some optimization if your data set's really big or if you're making a large image.
Yes. Yeah. So, putting these things together in a way that's efficient and that mostly always works in the way that you think they're going to work, highly non-trivial. Okay. So now what's the next thing that we do? We have step 1, default data set and a set of mappings from variables to aesthetics. Step is number 2 is 1 or more layers where you're actually taking the data and assigning it to geometric objects, perhaps with a statistical transformation and position adjustments of each of those layers and composing them on top of each other. Next is the notion of a scale, which is kind of coming back to that first point about how you're mapping the data, the variables themselves in the data onto the aesthetics. So a few examples of scale. I think scale is actually I found it very difficult to understand, and there were a few examples that helped me here. So an example of a mapping from a data attribute to an aesthetic attribute. One is the example that I gave before, which is based on when a certain data point was taken, like the variable of a timestamp, say for a download, that gets mapped onto a certain X position in the example of the histogram.
Right.
Right. And then on the Y position is a mapping from the count of the number of downloads in a certain time range onto a height of the bar. So the axes in this case, the x-axis, the y-axis, those are kind of like inverse scales. What they do is they help you reverse engineer, like as you're looking through the visualization, like depending on where within the visualization you are looking, you can decode information about the underlying data set. So you're saying, I'm looking at this bucket, and because of where that bucket is, it's telling me something about the time that I'm looking at within the data set. And this bucket has a certain height, like there's a certain top of the top of the bar is in a certain place. And that is also telling me something about the data set, namely how many data points that we have that fall within this bucket. So X and Y axes are both examples of scale, because they're helping you make that connection between the data and the actual aesthetics here. Another good example here is like a legend, where in this example, we said maybe each of our different layers gets a different color that's assigned to it, so that when I look at it visually, I can distinguish each of the episodes from each other.
Right.
Usually in that case, you'll have a legend, that's hanging out in one of the corners that helps you say, like, here's this color corresponds to this part of the data set. That's, again, helping you decode the aesthetics and how those map onto the variable that you're plotting. So scale, I think, is tricky, but hopefully those examples kind of make sense a little bit. So at this point in the visualization, you have to layer on that scale information so that somebody who's reading the visualization can say, like, oh, and there's also this kind of contextual, like, information that's not the data itself, but instead it's information that's overlaid around the data that helps me decode the visualization that I have.
Right. Okay. So in this case, actually, you could even say that the individual data points are not really represented in this graph, because you've got these buckets, and then the size of the height of the bars are representative of the number of data points in the bucket. But then you have these other pieces, like the x-axis and then also the y-axis at the very top, indicating the sum of everything in all of the buckets of a certain bucket time range, I guess.
Yes. So at this point in the composition of our stacked histogram, we're layering in, yes, that guidance about what all of this means. Because imagine a histogram that doesn't have an x-axis and it doesn't have a y-axis, and it's got some colors, but it doesn't have a legend that tells you how those map onto the different categories. Like, it's a data visualization, it is, but it's not telling you anything. Yeah. So
it might tell you the shape of some data, but it doesn't tell you anything concrete.
Yes, exactly. So scale, that's now step 3 of 5. So we're getting there. These last two, I think, are relatively straightforward, actually, in the scheme of things. Number 4, coordinate system. And this is mostly Cartesian versus polar. So Cartesian means like X on the x-axis and Y on the y-axis, and we're kind of making squares.
I had never thought of a polar stacked histogram. That's the one in a circle, right? Or that's not what we're talking about?
Yeah, no, that's what would be a polar stacked histogram? Maybe like a radar plot, perhaps, or something. Like, I was reading this through, and one of the observations, this was just an aside, was they were like, yeah, so a bar chart in polar coordinates, circular coordinates, is a pie graph. And I was like, oh, yeah, interesting.
Oh,
so
neat.
Yeah, so there's some of these like little fun things where it's like, yeah, so you take this type of plot and then you like change the coordinate system and it looks like this. And some of them you're like, oh yeah, that's a pie chart, I recognize it. But then other things I was like, I've never seen a visualization that looks like that, and that makes no sense.
Yeah.
So it's like we're starting to get into the like grammar layer here, where there are things that you're allowed to do according to these rules that will produce visualizations for you, but they might not make any sense at all, or they might be kind of against the conventions. Yeah.
So another thing I was thinking about earlier on is, so you've got, let's say, a linear y-axis. Could you make it logarithmic? And I don't think you could, because logarithmic only works on a continuous basis, and you've got these individual buckets that are stacked on top of each other. And so
you could still have a y. You could have a log y-axis, but there's an interesting aside that they do. This is on the topic, I think, of the statistical. I think this comes into play at the statistical transformations level. But people who are really interested in this should refer to the graphic because it's easiest to see this in visual form. But there are basically rules about if you're going to be transforming your data, you also have to transform your axes. Obviously, you can't like logarithmically scale all your data and then have your axes look like they're linear. But there's an order in which you want those scale transformations, or like logarithmic, exponential, whatever, all those transformations to happen such that it preserves the kind of like the readability of the information in the plot.
Yeah, exactly. That's exactly what I was thinking, because you could do it and it could be useful in certain circumstances, but it also could be misleading. Like, you might not, it would underrepresent graphically the bars that are closer to the top in our linear example with a logarithmic scale. And that's fine as long as I don't know, I guess as long as it makes sense to make a visualization like that. But if you just come in cold, not knowing how the visualization was made, you might think that those underrepresented top parts are just smaller, and they're not. And actually, another example I thought of when we were talking about polar coordinate system and a radial histogram, like a circle histogram, is that now your bars, now your buckets are not, they're not spatially linearly scaling. Because if you take a slice of a pie, the further out from the center you go, the larger of a slice you'd be physically taking. And so then I guess as a graphics maker, you have a choice to make. Do you have those be linear from the center going outward, or do you have them be almost, I guess, spatial, right? Like an actual slice of a pie would be. And again, if you're a viewer to this and you come in cold, you don't necessarily know how to interpret that data. And so I guess it's kind of on the graphics maker to use the grammar to make sensible plots that are easy to comprehend.
Yeah, I mean, one of the most interesting parts of this paper that I actually found was where Hadley Wickham starts to talk about how he thinks about defaults, because as we're talking about this, you can tell there's potentially many layers of complexity that you have to think about in order to compose a graphic that has all of these things figured out. And of course, if you're someone who's writing a programming language, you might need to have all of that complexity get captured in the package or in the language somewhere. But for somebody who's using it, you don't necessarily want to have all of that complexity front and center. Instead, you want to have a lot of it hidden away under sensible defaults. And so there's some places where Hadley Wickham is musing about what are the choices that you want to make about what the sensible defaults are. And if someone violates a default, what do you want to warn them? Do you want to just give them an ugly graphic and move on?
You need to make sure it's a conscious choice, because if they're violating a default without realizing they're violating a default, that might not be good.
Yeah. One of the asides I think I read somewhere was on the topic of how it's hard to make good plots in polar coordinates, rather, was he was like, yeah, maybe we should just like every time somebody tries to plot something in polar coordinates, just give them a warning. Be like, this is probably a bad idea, which I thought was a very opinionated statement, but I thought it was really funny. But yeah, there's all kinds of stuff that can go wrong at this point. Like I was reflecting on, as I was reading this and thinking about this stacked histogram example, this bug that used to confound me all the time when I was starting out in physics, and that eventually I got really good at just working around and accounting for. But here was the bug, was the plotting software that I would use that would be making these stacked histograms, right? It would, by default, set the scale of the y-axis according to the first layer that you plotted. So,
Oh,
so
interesting.
yeah. So what I would do sometimes, I guess this didn't come up in stacked histograms. It would come up in just like histograms that I overlaid on each other. So, I didn't have them adding up on top of each other, but instead just had like, they might be like translucent. And so I could see all the different distributions at once. But I would inevitably just plot the first one that comes to mind and then plot the second and the third. And, let's say that the peak of the first histogram is at 100. But the distribution for the second histogram is a little bit different. It peaks at 130. That's going to get cut off every time. So it had these, these gross plots where I have to like figure out which one is the highest one, and then you say that's the top, and then you set the scale according to that one, and then you draw the second one, but then you had to like redraw them so that they were always appearing in kind of the same order. And you didn't have people being like, what, your colors are all different. And it was just such a hassle. These are the things that like are so tough to get right for exactly these reasons. And then they give you really gross plots or bad user experience. Anyway, I digress. The last piece of a layered grammar component is a facet. And I think this one's one of the easier ones to understand. So a facet is the notion that we can have not just one plot that's, a single image in a frame and that's the end of it. But instead, many plots that we make are composed of different images that are tiled like next to each other. So we might have a histogram of all of our plots, let's say a histogram of all of our episode downloads, where the scale of the x-axis is the last 3 months. And then there might be another plot that we make at the same time that's same data, but it's the last 12 months. So that there might be multiple different views of the same, or maybe we would have the same download histograms, but the one on the left is from the United States and the one on the right is from European countries. So there's other ways that you can slice and dice your data and put them into multiple different images that sit side by side, or you lay them out in a grid or whatever, so that you can see in the entire visual effect as a whole is that you have multiple different types of data that you're comparing with each other in each of these different facets. So that's the last piece, is that you can arrange all of the different plots that you're making side by side.
It's interesting to pull this apart. As a native English speaker, I don't think about grammar very consciously very often, but in any other languages that I'm learning, I think about it all the time. As a consumer of graphics, I don't really think about these different elements very often, but obviously they're very important, and having a conscious understanding of them probably makes for better graphs.
Yeah, I mean, I think the vast majority of us have never written, fundamental data visualization software. And so we just take for granted that these things just work the way we understand. But yeah, I was finding myself like really, really, really thinking hard about what a stacked histogram was this weekend. That's not even like that complicated of a plot, really. It's something that, some days I make 30 of them a day and I don't think anything about it. But once you start to decompose it and you say like, what are the rules for making this visualization, and also that same set of rules when applied to other types of data that have other types of statistical transformations or other types of geometries, that it's still like mostly going to work and mostly give you something that looks aesthetically intuitive. Like, yeah, I find it like a really interesting thing that really, it's a thing I take for granted, but it stretches your mind as soon as you start to try to unpack it. So for those of you who are interested, we'll of course have a link to the source content, this Hadley Wickham piece on lineardigressions.com. It's got a decent number of visual examples of illustrations of some of these concepts. But hopefully this guided journey through a single type of data visualization gives you a greater appreciation for matplotlib or for ggplot or any of the other visualization softwares out there that you all use.
Linear Digressions is a Creative Commons endeavor, which means you can share or use it any way you like. Just tell them we said hi. To find out more about this or any other episode of Linear Digressions, go to lineardigressions.com. And if you like this podcast, go ahead and leave us a review on iTunes so other people get to listen to this content too. You can always get in touch with either of us. Our emails are ben@lineardigressions.com and katie@lineardigressions.com in case you have comments or suggestions for future shows. You can tweet us at lindigressions. Thank you for joining us, and we'll see you next time.